Okay, Savannah, here we go. We're on page 157, section 3.7. The title is Implicit Differentiation. We were just discussing what the word implicit means. As opposed to explicit, implicit means hidden. Explicit means pretty obvious. Implicit, not so much. So, implicit differentiation is hidden differentiation. Ooh. Bizarre.
Considering how much I read that,
yeah, it all could be hidden depending on how well you understand. But, let me see. Page 6.
Well, then,
yeah, it's a little bit. And it's a little bit taller than that. You can't see the bottom of it. But go back. Go back. It's kind of like that. It's just not straight. All right. Anyway, sorry about that. A little distraction. Okay. We need implicit differentiation because there are some curves out there that are not functions. Case in point, the one you're looking at, that's not a function. Yeah, it fails the vertical line test in several places. However, derivatives are things that when we find them and plug a value in, they tell us the slope of a line to a curve, the tangent line to a curve, right? Can you imagine that non-function curve that you're looking at there certainly has slopes at different locations? Tangent lines? Well, then we need to be able to find derivatives so we can find the slopes of those things in case we're dealing with something that's not a function. You're going, why? I thought the whole idea behind calculus was to study functions. And actually it is. If you'll notice the way the author drew that, he's got a blue function, a black function, and a red function. The trick is, and when you link them all together, you get that picture. And that picture together, I thought it was a single thought, is a non-function, but it still has slopes to it all over the place. And its equation is x cubed plus y cubed minus 9xy equals 0. And that's the equation of the whole curve. X cubed, is it plus y cubed?
Where is it?
Plus 9xy? Minus 9xy equals 0. And we don't spend a lot of time in prior courses to this. We don't spend a lot of time studying stuff like this.
It's x cubed, not squared.
Oh, yeah, that's a habit.
Where is that written at? It's right by the graph. Not the blue.
Left side of the graph.
On the page. Oh, we're looking at this one?
No, I'm looking at
Oh, I'm so confused.
this.
And there's, because that's a 7 and the other number was an 8, wasn't it?
Yeah.
Yes. Okay.
This is the one I'm looking at. Okay, all right.
Yep. Thanks, guys.
Okay, all right. So we don't spend a lot of time studying things like this. This is actually a variation on a conic section. Conic sections are something that we quit studying in pre-calculus in favor of other things that the powers that be think you need to know. And so we don't study conics anymore. We used to do it all the time. And anyway, we get these non-functions that have derivatives, so we need to be able to take the derivative of them. We'll come back to this one. I shouldn't have written it on the board. I'll write it on the board again. We'll come back to it when we learn how to find a derivative of something like this. There's a way to do it. It's pretty cool, actually. And it's pretty simple, actually. But you've got to think with me for a minute. And until it dawns on you what's really going on, and it may happen to you immediately, it may take 3 or 4 examples. You're just going to have to deal with the discomfort. We're going to do example 1, and I'm going to show you 2 ways to do it. It can be done 2 different ways. The one I just erased can only be done in 1 way. But if I were to consider this function, it's not a function, this relation, y squared equals x, that thing is, if you'll think about that for a minute, is really y equals plus or minus root x, right? And it's got to be plus or minus.
Yeah.
Because what this is the inverse of this. And you know what that looks like. That's just a typical parabola. The inverse of this is this thing right here is this reflected over the line y equals x. So this guy right here, which can be written like this, graphically speaking, looks like this. This is the top half of the square root of x, and this is the bottom half, and you get a parabola laying on its side, opening out to the right instead. So it's the inverse of this, which you're familiar with. This is a non-function, yet it still has tangents to it. And so what we could do, for example, with what we know right now is if I wanted to find the slope of the tangent at 4, there's 2 of them. There's the one that occurs here, and there's the one that occurs here, and they don't have the same slope. They don't even have the same sign on their slope. And so what we would do is, for example, we would take, if we did it with just what we know now, we would say, okay, if I wanted the one at the top point, which is 4, if you think about it, it's going to be 4. If this is 4, then this has to be 2. If we're talking about the top one.
Whoa.
This is the point 4,2. This is the point 4, -2. Right? And so if I wanted to find the slope of the line at 4,2, I would have to derive the function, which is the top half, this one. Right? You following that? So y prime would be 1 over 2 root x. Right, Connor?
Yep.
Okay, awesome. Okay. And then evaluate it at this x value of the point, which is 4, and the square root of 4 is 2, and 2 times 2 is 4, so that slope is 1/4. That feels about right. That's a pretty shallow line. Not like that. But if I wanted the other one at 4, which we're not used to considering because we're not used to looking at non-functions, then I would have to derive this one, which is -1 over 2 root x. And that's -1/4 at the point 4,2. And that makes good sense too. It feels right that they ought to be one leans left and one leans right, about the same rate, I guess, if you want to call it that. That feels about right. But I want to show you something really cool now that you can deal with both of these at the same time if you know how to derive implicitly. So this is the way we would do it conventionally, explicitly. We would consider each of these, root x and negative root x. Turns out that you can find the slope of any tangent line to this non-function with one equation, and it's not that bad to do. But it's weird. It's different than you've seen before, mainly because we're dealing with things that you've not dealt with before, namely non-functions. Here's what you do. Now I'm gonna derive this thing, and I want you to think about it for a minute before you say, what? This is how we derive this. Don't say what. Think. I'm thinking.
Easy peasy. Lemon squeezy.
Oh.
Okay.
Different. I turned my what to it up.
Is anyone, some of you I can see that you're trying to figure it out. Some of you I can see you already have. I'm trying it all. Try. Why would I have written this line here?
Oh, wait, which one?
This one.
Oh yeah, it's like
I heard it. What'd you say?
chain rule.
Yeah,
It's like
it is the chain rule.
Cosine theta, d theta, d
If you think about it, I mean, for a minute, you can define it as the chain rule, because when you define, what we're trying to find, folks, is the derivative of y with respect to x. That's what we're always trying to find, usually. Sometimes it's the derivative of p with respect to t, but still, it's the derivative of the dependent variable with respect to the independent variable. And yet, we have this term right here that is a function of the other one. It's backwards. Still, we can do it if we focus on what we're doing. The derivative of this is 2y. We bring the 2 down, reduce it by 1, so that's 2y. But because we're deriving y with respect to x, we also have to multiply it by this thing's derivative, which is dy dx.
I don't understand.
This chain rule.
The thing we're deriving is the function itself. This is the y. We're used to saying y equals something with an x in it, right? But we've got x equals something with a y in it, if you want to think about it that way. And what I'm saying is that you can derive every one of the terms in these types of functions. You can derive them with respect to x if you apply the chain rule. The derivative of this, the macro part of this, is 2y. That's the derivative of the macro part. But the derivative of the micro part is dy dx. Because the micro part is y. And what's the derivative of y? dy dx. Let me show you. If you have something like this, if we I don't know, 2x squared plus 4. Isn't the first thing we write dy dx? Isn't that the derivative of y with respect to x? Well, this is with respect to x, so we get 4x out of that because we only have x's to deal with on this side. We're applying that to this, the fact that when we derive this piece right here, it's a y, it's a function of y. So we take the derivative of the big part, the macro part, times the derivative of the inside, which is the derivative of y.
Why does it equal 1?
Because the derivative of x is 1.
That makes sense.
The derivative with respect to x over here is still just what it's always been with respect to x, which is 1. Yes?
So why would we derive x? Do we not put like dx dy?
Because that would be reversing the dependent and independent variable. We always derive the dependent with respect to the independent. Independent is x, dependent is y. And it's, you could, I suppose you could derive dx dy if you wanted to, and then you'd have dx dy equals 2y. But then you'd have the derivative of x with respect to y, and that reverses everything you've been thinking about. I'm trying to stick to stuff that you know. And the derivative of y is dy dx. This is still a function of y, well, not a function. It's still y in terms of x. We're still deriving all of this with y, as y with respect to x. And so when we run into deriving a y term, we apply the chain rule. 2y, that's what the big part is, times the derivative of the inside, which is dy dx. The derivative of any x terms is still what it always has been because we're still deriving with respect to x, and that derivative is 1. Then you solve for this by dividing, and you get a derivative. Now let me show you how cool this is. For the first time that you've ever seen this, the derivative of y with respect to x, it's got a y in it. We've never seen that. It always has dy dx equals something with an x in it. It's another function in terms of x, but this has got a y in it. Still okay. Because in this thing right here, if I want to find the derivative of, or the slope of the line at 4, 2, I won't be plugging the 4 in here like I'm used to doing. I'll plug the 2 in. And dy dx is going to be 1 over 4, if this is the y value, and it's equal to 1 over negative 4 if this is the y value that we plug in. Now we're plugging in y's because the derivative of y with respect to x turned out to be a function, well, not a function, turned out to be a relation in terms of y instead of x. It's okay. We just plug the y in. There just happens to be 2 of them. So we plug them in one at a time when we get those slopes. All at once with this slope generator. Now it's a little weird. It's a strange for your first exposure to this, but you'll get used to it. Yep.
When you say the derivative of y with respect to x, what else could it be with respect to besides that independent
Theta?
variable? Can it be derived in respect to anything besides the independent variable?
Nope. And sometimes the independent variable never even shows up. As you saw when we were trying to do theta sine theta with respect to t. Then we had to consider theta as a function of time and use the chain rule on that.
I don't remember doing that.
I think you're going to soccer.
Oh, that's a bummer, man. That's what you get for being an athlete. I don't know what to tell you. Well, we'll go on. I'll show you that one. Okay, if you look at example 2 with me, we'll come back to that strange curve of Descartes' time that we started out with. The next one is a circle. Also something we're familiar with, especially if it's centered at the origin. It's not very difficult to deal with. This particular circle has a radius of 5, and so its equation is x squared plus y squared equals 25, but it is not a function. Still, it has curvy places which have tangent line slopes. It's the best possible curve. I had somebody ask, do you guys know the definition of a circle?
Yeah.
Infinity points around the single point all connected or equidistant.
Infinite.
That's exactly what it is. It's the set of points equidistant from a given point called the center.
That's what I said.
The set of points equidistant from the given point called the center. Does that make good sense? All those points that are the same distance from the center, you link them together, you get a circle. But I asked a geometry class one time if they could define circle, just to see what they said. And the best one I ever heard that wasn't quite like that, it said it's a closed curve with the greatest degree of roundness. That's pretty good. Because there's a lot of closed curves. The one with the highest degree of roundness, whatever that is, but we all have a sense of what that is. I thought it was a good definition. It wouldn't work. It wouldn't work in a book because nobody can define roundness, but we all got a sense of it. Well, I thought it was good. Anyway, that's neither here nor there. Example 2, we've got this equation of a circle centered at the origin, x squared plus y squared equals 25. And this is not a function. Do you agree that if we worked at it, we could solve for y and it wouldn't be all that hard? Yes. I don't want to. Because I want to go with this implicit thing we just discovered, where you don't have to solve for y and deal with two different pieces. If we solve for y, we would be dealing with the top half of the circle and the bottom half of the circle as two different functions, and that'd be a little bit cumbersome. Well, there's a better way. That's what I'm trying to show you today. So if I decided to leave it just like it is, but I wanted to find the derivative of y with respect to x, we take these one term at a time. What is the derivative of y with respect to x if this is the only term? 2x. It's an x term, so it's just like you've always expected. What's the derivative of this term? You deriving y with respect to x. What is it? 2y dy dx. We saw that just a minute ago. Equals, what's the derivative of this term? 0. Don't forget, constants still have a derivative of 0. And then we take this equation and do our algebra skills solving for dy dx. Now you think about this. I think you guys are sharp enough to do this. All at once, dy dx is going to be negative 2x over 2y, which is negative x over y. You okay with that? Yeah. That's just algebra from there to there. This is calculus from here to here. That's the new calculus I'm teaching you today. When you derive a y term, you must consider the chain rule. I get your dy dx written. So we now have dy with respect to x, the derivative of y with respect to x, but it's in terms of both x and y. So you will need a complete point, but you can use any point on the circle that you want. So would you all agree, according to the Pythagorean theorem, that the point negative 3, 4 is on this circle?
Yes.
Negative 3 squared is 9, 4 squared is 16, 9 and 16 is 25. So negative 3, 4 is on this circle. So what's the slope at negative 3, 4? Let's first of all get a feel for where that is. Negative 3, 4 is about right here. So we can expect that slope to be positive. So I put in to my slope function, I put in negative 3 for x, because that's the point I'm interested in. So I have negative 3 over the y value, which is 4, and I get 3/4. It's positive, and that looks about right. Well, I didn't draw this in the right place. Negative 3/4 is actually about right there.
Can you explain to me the how you solve for that derivative, that third line?
I kicked the 2x over, made it negative, divided by 2y to isolate the dy dx. So all we're solving for is that fraction, so that we have dy dx equals something. But the thing is, it equals something in terms of x and y, which means you need the complete point to plug it in and find it. It's 3/4 here. Would you all agree that negative 3, negative 4 is also on this circle?
Yes.
If I go out negative 3 and down 4 here, I'm looking for this slope, and it should be negative, which it is. Because negative 3 is, negative 3 is positive 3, but if I plug in the negative 4 that belongs to this point, we get a slope of negative 3/4, which is what we expected. So what we've got is a slope generator for any point on that you can find on this. You can find a point on this circle, that'll tell you the equation of the tangent line through that point. But it's just in terms of x and y. It's okay. You just got to know both pieces of the point to plug it in. Okay, let's try another one. Oh, by the way, and I told you before that we could have, if you wanted to, we could go a conventional route and solve this. We could have said y is equal to plus or minus the square root of 25 minus x squared, the plus one being the top half of the circle, the bottom one being the negative being the bottom half of the circle. And then if you can figure out whether you're on the top half or the bottom half with any use, you can derive that particular function this way. You could derive this using the chain rule on the inside, and you would find the slope that way. We could do it by solving for y and then deriving both sides, but you're still doing implicit, believe it or not. Because if you did this, you would say, for start out, dy dx. What have you done? You've derived y. You've derived y. And what's over here is strictly in terms of x, so what happens over here is what you're used to doing. But still, you derive this side with respect to x, and you're deriving this side with respect to x. And I just did it all at once here. Okay. In this next problem, we have a transcendental function tied in with a regular algebraic function. You can't solve for x. You can't solve y. You don't have that option in this next one. The next one is 2y equals, well, actually, we could because it says 2y. Anyway, we're just going to go with this and do it implicitly. Oh, no, we can't. 2y equals x squared plus sine y. In this one, you do not have the option to solve for y, because when you have something that has a transcendental combined with a regular algebraic function in the same variable, you cannot isolate the y. There's no algebraic way to do it because this transcends the algebra. You can't get it done. You can't isolate the y. So you don't have that option. What?
Is there a way to not algebraic?
Not that I'm aware of. But we can, this is still a curve that has tangent lines, and we can still find the derivative by deriving both sides of y as y with respect to x. What's the derivative of this term? 2 dy dx. Good. Equals
Plus cosine.
plus cosine y.
dy dx.
dy dx. This is a y term. It has a chain rule too. The derivative of the sine of y is cosine y, but the derivative of y is dy dx. So when you're deriving a term written in y, you've got to remember to derive that function y with respect to x. This is what the implicit's all about. It's all hidden. Then you get, when dy dx shows up in more than one place, you get those things together on one side. The dy dx terms on one side, factor it out. And divide. That's it. So again, once you get to here, and that wasn't really that bad once you kind of get a feel for what you're doing. Now it's all algebra. From here, you got to solve for dy dx. Get your dy dx terms on one side, factor it out, divide by what's left. And now you've got dy dx. Why do you have to factor it out here? Because if you've got dy dx showing up in two terms, you can't solve for it until you can get it to show up in only one place, and that's the factoring skill. Then you divide by what's being multiplied by. Everybody clear? So this is a slope generator also involving x and y. You have to have the entire point, but if you can locate a point on this function, you can find the slope of the derivative there, or slope of the tangent line there. Okay. Should we go back now and look at that strange function we started with, see if we can derive it now?
Sure.
We have x cubed plus y cubed minus 9xy equals 0. And that is a non-function, but it still has tangent lines. So let's go about deriving y with respect to x. What do we get? 3x squared.
Plus 3y squared dy dx.
Good. You guys are picking it up.
Minus
What?
dy dx.
Nope.
We're not using
No.
product.
Yeah, product.
Yeah. Okay.
You're gonna run into this a lot.
So it would
X.
just be
First,
1
dy dx.
dy dx times the derivative of the
Plus.
second plus
Y.
y. Because the derivative of the second times the derivative of the first, if you leave the 9 out here, the derivative of the first is just 1. Because it's an x term. Everybody clear?
Yes.
Derivative of 0? Okay. That's one of the biggest mistakes people make, by the way. If there's a constant over here other than 0, they always just want to leave it a constant. It's not. It's going to be 0. You're right. So if I save myself a line by distributing this -9, I get this and this
Wait, is it minus?
What?
Why did the 9 say 9?
Because it's derivative of 0.
So if you
So
added
why did
it,
it just get rid of
it'd
it?
be 0.
Look, you decided to derive this without holding the 9 out. I just always hold the 9 out so I can deal with the variables because I understand because of the product rule that 9 is just going to belong to whatever I get by deriving this. If you decide to do negative 9x times y and derive that and let this be part of the x, you'll get the same thing. It'll be the first times the derivative of the second plus the second times the derivative of the first. I just like to deal with it later. It's just me personally. You can let that negative 9 attach to either one of these as part of the function, and it'll work out fine. You don't have to distribute. I just like to focus only on the variables. It's just a personal thing. You can derive and let that be part of x all you want. It's okay. I just don't. I just let the constant hang out here until I deal with those other guys, and then distribute it. It's just me.
So you don't have to do the product rule with each of them individually.
No. Because this is a constant function, yes, but it's derivative 0. So when you write down the term where this gets the chance to be the derivative, you won't have a term. Is everybody okay with what we've done up to here now that we've had that explained about the 9? Are we good or not really? Yeah? So we freed up, by doing that distribution, without saving myself one, by distributing there, I have freed up everything that was inside the parentheses from moving around. Now the next thing, just like over here when we were right here, is get your dy dx's on one side and everything else on the other. After doing this once or twice, you're going to be able to do this next step without this one. You just be able to look at it and go, I know what I want to do. And you'll factor it out and divide all at once because you guys are sharp people. This is not a dy dx term. He's got to come over. This is not a dy dx term. He's got to come over. Factor out dy dx. Is it okay if I factor that out and divide at the same time?
Sure.
Will you be okay with that? Do you understand what I'm doing? I'm going to factor that out and I'll have 3y squared minus 9x and I've got to divide by that. We could knock a 3 out of everything. If we're going to use this to generate a bunch of slopes, we probably don't want that 3 hanging out. So it would be 3y minus x squared over y squared minus 3x.
Nice.
Okay?
This is fun.
And if you have a point on that strange looking curve we first encountered, if you know there's a point on there, then you can find the derivative. What would happen though if we tried to find the derivative when x is 3 and y is 3? It is a point on there.
You divide by 0 and everything.
You divide by 0, and which means there's no derivative at that point. What kind of derivative what kind of tangent line must it be in this curve?
Vertical.
Must be a vertical one because there's no corners or cusps or discontinuities in that thing. The only other option is when you find the derivative is undefined, and that would be at the point 3, 3, I should say. If that happens, if that's a point on the curve, and it is, you get a vertical tangent. And if you'll go back to that page, you'll see that that occurs at A. That's the point 3, 3.
There's no way that's 3, 3. It's like right next to 5.
You're dumb, Jacob.
No, he's got a
No,
point.
he's okay with that. The other one, the y value might be 3. Oh, okay. All I know is that if this is the derivative, if you're at x equal or x and y are 3, 3, you get an undefined slope. So you're right. That may not be 3, 3, but where would 3, 3 be? That wouldn't have a non-slope. It would have two slopes. One on the black one and one on the blue
But
one.
it is saying it's not differentiable in A, so it thinks that's 3, 3.
So apparently that's.
Yeah, maybe it's a poorly drawn graph. Maybe it just has that shape. I
It
don't know.
used to have right there an asterisk, not trying to scale.
Well, we weren't actually supposed to do this one, so perhaps it's completely drawn out of scale. It was just to
They're
give you
just
the
like,
concept.
yeah, just wing it.
Yeah, you could have been.
Nobody's gonna look at this.
Anyway.
Nobody's gonna care.
Can you see that at the point 0, 0, it is also undefined? Because the derivative there would also have division by 0, and if you look at the curve at 0, 0, that one's actually drawn pretty well. That one has also got vertical
I
tangent.
really hope so.
Vertical and horizontal tangent. All right, anyway, we weren't actually supposed to do that, I just wanted to come back to where we started so you can see it finished. Okay, we've got a couple more to do. The next one actually has some practical application. Imagine that.
Wow.
Are we gonna do satellite dish problems?
Like find the exact.
It's quite possible. Listen to this little blurb of explanation so you can see that this has actually applied routinely for people who do anything with lens work. In the law that describes how light changes direction as it enters a lens, by the way, we're on page 159, Savannah, right at the top. Talks about how light enters lenses. The important angles are the angles the light makes with the line perpendicular to the surface of the lens at the point of entry. So if you're looking at that picture, that one to the left of example 4 there, that graph, maybe you can understand this a little better. So let me try this again. It describes how light enters, or how light changes direction as it enters a lens. The important angles are the angles the light makes with the line that is perpendicular to the surface of the lens at a point of entry. And we're talking about the red line being the tangent. The normal to it is the light ray coming in at that point. And if the light ray is angled along that black line, it will enter the lens as though the lens weren't even there. But if you get a light beam if you've got a curvy lens like this, maybe one in your eye. I mean, optometrists and ophthalmologists are dealing with this stuff all the time to try to fix your eyes or to design a lens that will fix your eyes. It's pretty amazing stuff. If you've got a lens like this, that's really crappy drawing, I know, just go with me. If you wanted to know right here, if this was the tangent line and the light were coming in right perpendicular to it, then this would go right through the lens like this. However, if the light were coming from here at this angle right here, then we would want to know this tangent line, well, I did draw that very well. This tangent line right here, and this would come in, it would come right there, and as soon as it entered the lens, I did that wrong. I tried to make it perpendicular to the wall. Let me draw a better lens. Sorry. Hang on. I'm just gonna draw this part of it. Okay, there's your lens right there. When the light comes in right here, so that this tangent line comes in perpendicular, go right through it. But if the light's coming in at this angle right here, and this is your tangent line, then when it hits this line, right there at the lens, it will bend perpendicular to that line and come through the lens that way. Okay, so the normal to this determines the angle. In other words, if we took this tangent line right here and we drew the normal to it, then this line right here in the lens would be parallel to it. Normal to it at that time.
But if you have light coming in from way off to the left, it's still going to bend at that same angle.
It's going to bend at the, yes.
If it comes in
And sometimes that angle is so sharp that it will come in here and it will reflect off. It won't even go in.
but it goes the other way.
It goes the other way?
Yeah, you have it bending back the same way from the tangent. It's supposed to bend the other way of the tangent.
Here?
No, the other way.
Here?
Yeah,
Supposed to bend like that?
yeah.
I mean, that makes
At
more
like
sense.
half the angle almost.
Because if everything's supposed to go to
Is
the
the
same
angle of incidence and angle of refraction, is that what we're talking about? Possibly?
Yeah, that's what it shows in this thing. It shows the,
Everything goes.
after it comes in, it goes to the other side of normal.
Dude, our eyes go well designed.
Bounces off that way
Yeah,
because it's got an
But
angle.
it's not as big of an angle.
Okay. Well, that's what I get for freehanding the drawing. All I'm saying is, and I'll be honest with you, it's been a long time since I studied the physics of lenses. But what I'm telling you is, it is dependent upon the angle that the ray's coming in and the tangent line to the curve where it enters.
And that's where the math comes from.
That's where the math comes in. And so I'm sorry, I'm a bit deficient on the physics, but it does bend according to those rules. Anyway, so we need to be able to write equations of normals. That's what I'm saying. We've done that before. But we need to write equations of normals to curves that are not functions now, because we're in implicit differentiation section. So here's our equation. X squared minus xy plus y squared equals 7. X squared minus xy plus y squared equals 7.
That's X minus.
Do you see that it would be really difficult to solve for y if that's the route you chose to take? You could do it because this is not a transcendental. It would require the quadratic formula. I don't want to do that. So we're just going to leave it the way it is. This is an ellipse, non-function, and it says find the tangent and normal to this ellipse at -1, 2. Let's verify that -1, 2 is actually on this function. Not function, this curve. This would be 1, right?
Yep.
It would be -1, if I do just this part, -1 times 2, which is -2, but it's really negative, so it's +2, plus 4, and that is 7, so that is a point on the curve. Just verifying. Sometimes they'll only give you the x and you gotta plug it in and find the y. Anyway, all right, so we're convinced that's a point on the curve. We have to find the equation of the tangent line and the normal. So we've got a point for both of them. We need a slope. So we need dy dx. And we need to find it implicitly. What do we get?
2x.
Is it okay if I do this? This is the one I like. Is that okay if I do that?
Yeah.
What would it be?
1 times dy dx, but can you do
Not 1.
dy dx?
X plus y.
X dy dx. I heard it.
Y plus.
Because we're using the product rule. Come on, folks. You with me here? It's a product. First time's the derivative of the second.
Oh, are we not finding the whole thing or just, okay. We're finding the whole thing step by step,
Yeah, implicitly.
implicitly.
So this chunk right here, I'm holding the negative out here, so I don't have to think about that right now. I'm deriving x times y. It's a product.
Yes.
First times the derivative of the second. Then
Plus.
plus y, because the derivative of the first is an x term whose derivative is 1.
Cool. Oh. 2y dy dx.
What goes right here? Plus
Plus.
2y dy dx equals 7. 0. Not 7. Don't stumble there.
Constant is always 0.
Again, I'm going to save myself a line. If I was doing this in an Algebra 1 class, we would write the next line and distribute that negative, but I think you know what's going to happen here. I always wait and do that with my pencil eraser because I don't want to think about that negative while I'm focused on taking that derivative. If you try to do both at once, you generally make mistakes. So this is what I get, and then I need to do, I'm gonna see if you guys can do this all at once. I'm pretty sure you can. You're pretty sharp people.
I
I'm
bet.
gonna go right to dy dx. It's gonna have these two kicked over to the other side on the top. Do you see that?
Hold on.
These are not dy dx terms. They're gonna go to the other side.
So let's immediately go over.
And then I'm going to divide by what would be left if I
So you.
factor that out. Would be 2y minus x. That's what I'm dividing by. Did I lose anybody in the algebra? So now I have a slope generator in terms of x and y, but that's okay because we have a whole point.
It looks like.
So at the point, at -1, 2, m, the slope, equals 2 plus 2, are you with me? I'm doing the plug-in. 2, -2 times -1 is positive 2, over 4 plus 1, because it's a -1. Y'all see the plug-in? Which gives us 4/5. So now we have a slope at that point. So the tangent line is y equals 4/5 x plus 1 plus 2, which is 4/5 x. And 4/5 times 1 is 4/5 plus 2, which is 10/5 is 14/5. That's the tangent line. How do we write the normal? That's what we're really interested in. Y equals -5/4. Got to change the sign and tip it over. X plus 1 plus 2 gives us -5/4 x. This is -5/4 plus 8/4, 3/4. Gives you the equations of the tangent and the normal. What do you think? You okay so far?
Yeah.
Or not? You understand this implicit stuff? Whenever you're deriving a y term, throw a dy dx on it.
Derivative of y into y dx.
Okay, now we're gonna find a second derivative. Yes, you have to do that for these as well. Even though you guys really, right now, don't have a use for second derivatives, all they ask you to do is find them, so you do what you're told. There is a use for second derivatives. We're not gonna discuss that now, you're just gonna practice the skill of finding it. Finding the second derivative implicitly has an interesting hidden part to it. Please don't look at the solution. Let's see if we can come up with this on our own.
Stop. Say no. Turn around. Walk away.
Okay, so in example 5, please don't look at it. We're trying to find d squared y over dx squared. That's ultimately what we're trying to do. That means the second derivative, by the way. I forgot to tell you that.
Okay, I know we've asked this
Why
before.
is it dx squared, not square x?
Yeah.
Ask Google sometime. I don't have time today.
Just, I know we've asked.
Just listen. We got to hustle here. The the relation that we're trying to figure out the second derivative of is 2x cubed minus 3y squared equals 8.
That's our.
2x cubed minus 3y squared equals 8. And we wish to find the second derivative of this, which is going to have to be derived implicitly. So our first derivative, dy dx, got to find that first, just the way we've been doing it all day. What's it going to be?
6x squared minus 6y dy dx equals 0.
So dy dx is going to be
Equals negative 6x
X squared over.
It's gonna be positive x squared over y.
Sorry.
that's a lot of math inside your head. That's a lot of math. You want me to show you?
It's like,
You need to see it?
honestly, I kind of. You just.
It's negative 6x squared over here divided by 6y. The 6's go with sort of the negatives. We end up with x squared over y.
Yeah, because you subtract the first one by negative. Okay, I got the negatives, but I didn't look at the.
Sonny, the intermediate step here is to kick this. What we had is negative 6y dy dx equals negative 6x squared. So when I divide by this, the negatives and the 6's go, and I end up with x squared over y. Does that make sense? If you can't do it that fast or you're worried about losing signs, please take the extra step.
I will.
Okay? Okay, so this is our dy dx. We wish to find the second derivative. What is the derivative of this?
Squared y dx squared.
Right, it is that thing. The derivative of the first derivative is the second derivative using proper notation. So this side's derivative is d squared y over dx squared equals, and now to find the derivative of that, we have to derive this side. What are we going to have to use? Not product.
Quotient
rule. Can anybody tell me the first term?
So y, 2xy.
2xy. It's the bottom. Bottom.
Constant, we're just.
Times the derivative of the top, which is 2x, because it's an x term, there's no dy dx here. You see it? Minus the top
Squared dy dx.
times the derivative of the bottom, dy dx,
All over.
all over y squared. So that's the second derivative, right? Wrong, we're not done. You can't write the second derivative in terms of the first derivative. The second derivative has to be written exclusively in x and y, not the derivative of y with respect to x. So what do?
We plug in x squared over y.
Yes, you replace it with this. That's the extra little piece.
Oh my gosh.
Oh, so we have a chain function.
So we plug that in so that it's all in terms of x and y. So d squared y with respect to x squared is 2xy minus x squared, or actually x to the fourth over y squared. You all agree with that?
Yes. Wait. Yes, I got it. Okay.
Everybody clear on that? Now, I would give you full credit for that. Is there any way to simplify that at all? I mean, really, truly, you're not supposed to leave fractions within fractions. You're not supposed to do that.
What do we do?
But if you do, and you've applied the calculus correctly, and you got it right to here, I'd probably give you full credit, because I'm interested in how you do the calculus. But let's say that I ask you to simplify, what would you,
Flip over
You
and.
gotta get rid of those y's.
we need a common denominator for the numerator.
We need a
Three times it
freaking.
by y.
Times it by y.
So d.
That's the numerator. Do you agree?
Yes. Okay, yeah, we got times. Oh,
Do y'all see that?
I see it.
This is the numerator, and I'm multiplying by the reciprocal of the denominator over here, putting it here. And what we end up with then is 2x, y squared minus x to the fourth over y to the third.
Y cubed. And then we leave it there.
You could.
Can we?
You could also put y cubed under both of these and cancel two of them out of that one, but either way, doesn't matter.
How did we end up getting y under 2xy minus?
Because we replaced this dy dx in our second derivative, we replaced it with this. And
Right.
when I multiplied x squared times x squared over y, I got x to the fourth over y.
Right.
That's how we got the y here.
Yeah, how did we get it?
This right here, this was over 1, and I multiplied by y over y, so that I'd have a common denominator for my numerator.
She made a fancy one. That's literally what it is.
It is, it's
That's
a
how I
fancy,
remember
fancy
it.
way of writing 1.
Like, all right.
This, forget about this part right here, just look at the numerator. If I wanted to add those two things together, they both have to have a denominator of y. So I multiplied this one by y over y, so his denominator can be y. And then I have 2xy squared minus x to the fourth all over y, times the reciprocal of the denominator, and that gives us.
Why would it not be y cubed?
Well, my question to you is, why would it be y cubed?
Oh, because you have the y squared later. Never mind. I was.
Okay. Yeah, I've got a y here from the numerator times y squared gives you y cubed at the bottom. We okay with that? So that was crazy. So a second derivative, folks, cannot be left in terms of the first derivative. You've got to come back and substitute that and clean it up. So your second derivative must be in terms of exclusively x and y as well. You cannot have a variable that is the first derivative. You have to replace it. Just saying, that's where it goes. Okay, I want to do one more thing and then I think we'll be done. He spends an entire page and a half talking about the stupid power rule again. We've already discussed it several times, so I'm not going to talk about that. You guys can, you know how to do it. What I would like to do is the exploration. Okay, I'm hoping to get through this, and if we don't, we'll finish it tomorrow, but I think we can get through it. If we go fast and you stay with me,
Yeah, we don't have school.
on like Monday then.
You can just.
Okay, so we have, I have
Zoom
Zoom,
call.
that's on my brain.
Yeah, no.
X squared minus xy plus y squared equals 4.
It's like, oh.
Do that.
Okay.
It's minus 2xy.
Okay, all right, listen up. Is this plus?
Yep.
Okay. Here's what we're exploring here. It says, consider all the points x and y satisfying this equation. What does the graph of the equation look like? You can find out in two ways in this exploration. First of all, do you think we could solve for y in this?
Yeah,
It would be pretty tough. It would be pretty tough. Shh. So we're going to follow the steps that they ask us to do in the exploration. Use implicit differentiation to find dy dx. Are you surprised? Let's see.
It looks kind of like a difference of 2 squares.
Possibly. Okay, take a look here. It's not a difference of 2 squares, but that may come up, something like that. So how do we derive implicitly? 2x minus. You want to not distribute, you not want to hold it out, that's fine. Minus 2, the first times the derivative of the second, plus the second
Y.
times the derivative of the first.
Negative 2.
Is that okay? Plus
2y derivative.
equals
0.
0. Don't forget that part right there.
Since you're 0.
Now we're going to do that really tricky math here, all in your head. The y dx is going to be, these guys got to get tossed over, so it'll be 2y minus 2x, and then I gotta divide by what happens when I pull these out of there, and that's gonna be negative 2x plus 2y, or 2y minus 2x.
And which I want to
Look
think
at
that
that.
derivative
One.
is
Did that surprise you a bit?
Yeah, a tad.
Did me. Actually, it didn't, because I've done 6 words. But that's a surprising result. What does that mean? Take a look at number 2. Knowing the derivative, what do you conjecture about the graph?
It's a line.
It has to be a line, because the slope is always 1. It has to be a line with a slope of 1.
That's a really fancy way to write X.
Y equals x.
Y equals X.
You think that's what it is? Maybe it doesn't cross at
Something
0.
along those lines.
Hang on
Plus
here.
4, minus 4.
So, okay, so knowing what you, listen, that this is a line whose slope is 1, that's all we know, right? That's what you're thinking? Okay, now listen. What are the possible values of y when x is 0? Possible values of y when x is 0. So we come back to the function itself. If I let x be 0, what does this thing turn into?
2 negative 2. Y that goes away.
You get y squared equals 4.
Which is 2.
Which is 2.
No, it isn't.
Plus or minus 2.
It's plus or minus 2. How can you have a line whose slope is 1 that has a value, that has a point on it that is 0, 2, and another point that's 0, negative 2?
There's 2 lines.
Parallel lines. What?
If x is 0, we get a y of 2. That's what we just showed. But if x is 0, we also get a y of negative 2. That's 2 different points. And yet the slope is 1.
Big line.
That's a really big one.
Okay, listen. Shh. So it says that should flummox you a little bit right here. Just knowing, yeah,
I
you're
have
going,
been
what?
flummoxed.
And then some of you said parallel lines. How could we prove that? By applying some algebra that occurred to him, but didn't anyone else, but he stated it wrong. I know what he was thinking though. I think I did.
This thing.
This right here, if you think about the algebra of it, can be factored into what?
X minus Y
Oh,
squared.
yeah.
X minus y squared
What is that called?
equals 4. That's called a perfect square trinomial.
Oh,
Because it factors into it. The binomial is the same thing.
That's
If
what
we,
I was
listen,
thinking.
hold it. If we continue to solve this for y, this thing, first thing we would do is square root both sides,
Oh,
and
yeah,
we
I
would
know
get
the difference.
x minus y equals plus or minus 2, yeah? And so y would equal
Plus or minus 2 minus
X.
x
Plus or minus 2.
plus or minus 2.
Because if we move the X, or we get negative X.
That
minus 2,
is
and
2
then-
different lines. One of them crosses right here with a slope of 1, and one of them crosses right here with a slope of 1. So you were right. This thing produces 2 parallel lines. Who knew? That's weird. It's strange, but it works out. It's kind of a cool little function. Okay? Well, it's actually not a function, as you can tell. That's a non-function. But it produces 2 parallel lines, which is rather interesting. Okay, then he wants to revisit the power rule with irrationals and fractions. We already know how to handle that, so I'm not gonna do it for you.
Fire this go. Put it in the backpack.
We made it, barely. Okay, so this assignment is given. Listen, I have to come to school tomorrow. You don't. That means you use tomorrow to do this. I'm not giving you Monday. We're moving on Monday. So get it done and bring me your
We have
questions.
3 days to do it. And I'm gonna.
There you
have
go.
a lot of-
Bye now.
I get to drive.